Greetings, detectives. Mrs. McKay here, and it's time to work on clue, learning target clue 5-4. That's about interval and set notation. Now, we've already talked a little bit about interval notation, and then we're also going to review set notation a little bit more thoroughly. So let's go ahead and start with filling in our graph, because we're learning these two types of notation not to just learn them, but because we're going to use them to describe graphs. So we're going to fill in our learning target clue, not our graph. So let's go ahead and start by writing, I can describe the graph of a function using interval and set notation. All right, so that's our learning target. I can describe the graph of a function using interval and set notation. So the first thing we're going to need to do is just review a little bit and then learn some set notation, and then we're going to practice describing graphs. Okay, so that's what we'll be doing. Let's go ahead and get started quickly with just a quick review of interval notation. Remember that interval notation is what I introduced to you when we were talking about the domain or range of a graph. But really, anytime we want to describe an interval on a graph, it could just be one little section, like where the graph is increasing, or where the graph is constant, or where the graph is decreasing, or what the domain of the graph is, or the range of the graph. We can use interval notation. And if you remember, interval notation has different symbols. We have this opening parenthesis, which means that we're going to have two numbers after it. So we could have infinity or negative infinity, or a number after this opening parenthesis. And all it means is that the opening parenthesis means that the first number, which is the start, is not included. And then if you have a closing parenthesis, that's for the second number. And again, it can be the same types of numbers, but the second number or the last part of the interval is not included. Okay? So an example could look like this. Negative infinity to 3. And all that means is the interval starts in negative infinity and we never reach negative infinity, so it's a curved parenthesis, and then it ends at 3 but doesn't ever reach 3, so it doesn't include 3. So that's one example. Brackets mean the same thing. Opening means included. Okay, the first number, the starting number, is included, and the closing bracket means the closing number is included. So we can have any combination. We could have something that looked like this, which means that we start at 4. Sorry, that shouldn't be. Should be curved. We start at 4, and the interval goes on until into infinity. The other thing to remember is that if we're measuring our x's, then that's our domain. If we're measuring our y's, that's our range. As we move forward, we're going to be talking more about intervals of increasing and decreasing, and when that happens, we always just look at the x values, not the y values. So just be aware of that as well. So here's an example of something written in inequality notation. X is less than 3 and x is greater than negative 4. So that means that we're starting at negative 4. So if you think about on a number line, we're going to say that this is negative 3 and this is 4, and it's going to be an open circle, and it's connected. So that's the interval that we're talking about. So if we were going to write that in set notation, we would say that the starting place is negative 3, sorry, not, that's a positive 3. And this is a negative 4. So this should be, so I did this totally wrong. Let's try again. I was doing this so fast. This is negative 4. This is 3. And x is greater than negative 4, but less than 3. If I had been smart, I would have written it this way so that we could have read it from left to right. Like that. But if we were going to write it in set notation, I'll put it up here. We will say that that's curved. We have negative 4 and 3. So we're going from negative 4 to 3, and it's not. Negative 4 and 3 are not included. Let's make this, put a line underneath that. And this one, we're going to say this would be the range. We're going to say that y is less than 5, so that means that it goes forever, starts negative infinity, and it goes to 5, and 5 is included. All right, so that's just a quick review of interval notation. Now, let's talk about set builder notation, or for short, set notation. First of all, set notation, a set is a collection of unique elements, meaning there are no repeats. And when we usually look at sets, like when we were listing the domain of a set, we would list them in a roster, a list of elements. And we use these curly braces. And so here's an example of a set. Curly braces 1, 2, 3, 4. And that means all the, just 4 elements in this set. 1, 2, 3, 4. All right? And here's another one. A curly braces 1, 2, 3, 4 with the 3 dots called ellipses after it, which means that it goes on into infinity. So it's basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, forever and ever. But if we wanted to list all of a domain, for example, if we had something like this, and we wanted to include everything, and we wanted to list it all, that could be difficult. The other thing is that it's not just 3 and 4, it's everything in between 3 and 4. So that would take, we wouldn't be able to list every single element in the set. That's why we use the graph, because it includes everything. Well, using set notation allows us to do it as well. But first of all, there are a few things that we're going to need to learn. For example, we're going to need to learn what some of these symbols mean. So this R, capital R, means real numbers. Okay? And pretty much real numbers are everything that you've ever known anything about. It's going to be all the positives, all the negatives, all the fractions, all the irrational numbers like pi, the non-repeating decimals, every single number that you've ever had any experience with. Those are the real numbers, okay? So in this situation, this would be 3 on all of the real numbers, right? Z stands for the integers. Now, I'm not sure why they picked the letter G or Z, except that I believe that the I represents irrational numbers, and that's why. But Z represents the integers, and integers are all of the positive and negative numbers that are not fractions or decimals. Okay, so that's going to be things like, if I had a number line, 0, 1, 2, -1, -2. It's not going to be the stuff in between. It's just going to be those sort of whole numbers without any fractions, okay? That's integers. N stands for natural numbers. Natural numbers are the numbers that are, we've often called them our counting numbers. So that's going to be 1, 2, 3, 4, not including 0. So it's the positive half of the integers without 0. Okay? That's what the natural numbers are. Whole numbers, that's what the W stands for, are 0, 1, 2, 3. So whole numbers are all of the numbers that are 0 forward. Okay? So the integers with 0. So those are some of the terms that we'll use to describe our sets. Okay, so these are each sets of numbers, and each one is inside the other. If you think about a Venn diagram, here's my real numbers. Okay, inside my real numbers are my integers. Inside my integers are my whole numbers, and inside my whole numbers are my natural numbers. So they're all sets or subsets of real numbers, but even the real numbers are a set. Okay, now this E that you'll often see written like this means element of. Okay, so we'll see that E that basically says this variable is an element of a certain set. Okay, so it's a member, an element of that set. And then you'll also see this straight line. It's not a letter, it's a straight line, and that means such that. Such that. Okay? Sometimes you also see it as a colon. All right? But for this time, we're going to just be using this, the line. So now let's read what we have written here. This is set builder notation, and we're going to use it to describe a set. And the set looks like this. Let me write it over here. If we were going to write the roster, it would be 2, 3, 4, 5, 6. Okay, so that's our set. And if we were going to describe it in set builder notation, we would say all X, that's what this stands for, all X is an element of this part. Actually, I probably should do this in a different color each time just so you can see it better. So is an element of the integers okay, so that's basically saying what main set is X coming out of, okay? So X is an element of the integers, and then we have this line, and this is sort of our defining part. This part right here is the defining part, okay, that tells us how we're going to define it even more, such that okay, and the last part, and we already know how to read this, X is less than 6 and greater than 2, or the other way around, is greater than 2 and less than 6, all right? So all X is an element of the integers, so all X is an element of the integers such that X is, we'll say, greater than 2 and less than 6, okay? Greater than 2 and less than 6. That's set builder notation. That's set builder notation. So we're going to use that to describe intervals. All right, so we're going to use set builder notation, and we're also going to use interval notation. Okay, so what I'd like you to do now is go ahead and write a key idea at the bottom of the page here. Okay, write yourself a key idea to help you remember a few things, and then we're going to flip your paper over or use the second half if you just printed it off, and we're going to do that 5-6 worksheet. So go ahead and do that. Write yourself a key idea and then flip your paper over. Okay, so we are continuing on. Now we're looking at this back side of our paper, and we're going to work on this little activity. All right, so it says, given the graph f of x, answer the following questions unless otherwise specified. Restrict the domain of the function to what you see in the graph below. Approximations are appropriate answers. Okay, so approximations are appropriate answers. So here we have a graph, and we've got a starting point, and we've got an ending point. And those, I'm going to say that the red dot is included. It's included, all right? It's not open, that it's actually included, all right? So it's a filled in circle. So we're going to start, and it's going to say, what is f of 2? What is f of 2? Well, all that means is when x is 2, what is the outcome? So when we put 2 into the graph, and that means for x, because x is always our independent variable, and then our dependent variable is our y, it's the y-axis. We put x in, and what do we get out? Okay, so when we put 2 in, what do we get out? So the way that we figure that out is we say, well, when I put 2 in, here's 2. What do I get? Well, I'm going to go up the graph, and I'm going to see that f of 2 is 6. Okay? So when x is 2, y is 6. So f of 2 equals 6. Okay? And then it says, for what values, if any, does f of x equal 3? So that means, what could x be, or what is x when the output is 3? So now I'm going to look for the 3 on this graph. I'm looking for 3, meaning when the y value is 3, when the output is 3. And do you see it? It's right here. Well, what's x when y is 3? Well, f of 0, right? X is 0. F of 0 is equal to 3. So what values, if any, does f of x 3? F of x equal 3? Well, when f of 0 is equal to 3. When x is 0, f of 0 is 3. All right? Next question. What is the y-intercept? I'm going to let you figure this one out. What is the x-intercept? What is the x-intercept? See if you can find the x-intercept. And remember that you write it as a point. You write it as a point. Did you find it? It's right here. Right? That's where this function crosses the x-axis. And it crosses at -1, -2, -3, -4. So -2, 0, because y is 0, right? What is the domain of this? What is the domain of this function f of x? So remember, the domain is our x value, and now we're going to write it 2 different ways. We're going to write it in set builder notation and in interval notation. So let's go ahead and do interval notation first, because that's the one you're most familiar with. We're going to say that it starts at and includes this point. So it starts at -4. Remember, domain measures along the x-axis. So we started at -4, and -4 was included. And we went until, let's see, this goes all the way down to 6. And 6 is included as well. All right? So that is in interval notation. But now we're going to write it in set builder notation. Set builder notation. Well, first of all, does this line include every single possible number between this one and this one? That means, is it a part of the real numbers, the integers, the naturals, the whole numbers? What is x going to be an element of? What is it going to be an element of? So we're going to start by writing our little curly cues while you think about what it's an element of. So we're going to say x, all x, such that x is an element of. What symbol should I use? Look, turn your paper over and decide. Should I use real numbers, integers, whole numbers, natural numbers? Which is it? It's real numbers, right? Because it's everything. It's every single possible thing in between. So it's all the real numbers. X is an element, all x is an element of the real numbers such that, and now we're going to say what are the defining factors, because it's not all real numbers. There's only certain parts of the real numbers. And we'll say that x is greater than 1, 2, 3, 4, -4, and less than 6. Excuse me. Okay, so interval notation, set notation, all right? We need to be able to do both and understand both. Now, let's do number 5. On what intervals is f of x greater than 0? Is f of x greater than 0? On what intervals is f of x greater than 0? So that means the value of the y's are greater than 0. So when is it greater? Which is really going to be the same question as, actually, no, it's not. So when are the y values increasing or greater than 0? Meaning, when is it positive? Okay. So let's look at this and decide, when is f of x greater than 0? Well, it's greater than 0 from here all the way up, right? It's not greater than 0 down here, is it? It's greater than 0 up here. So let's go ahead and first mark it using set builder notation, shall we? So let's see. Is it going to include this point, which is -2? No, it's not. So we're going to say f of x is greater than 0 when from -2, but we're not including the -2, until 6, and we'll include the 6. Okay, so that's interval notation. So from here to here, okay, when x is 2, -2 to 6 is where f of x is greater than 0, where the value of f of x is, or the value of the y value is greater than 0, okay? Not when x is greater than 0, but when the value of f of x, okay, when it's plugged into the formula, when it's greater than 0, except that it doesn't include the -2 when x is -2, okay? Now, let's write it in set builder notation. So again, we use our little curly braces. We're going to say x is an element of, and again, it's still the real numbers, such that, okay, that's not a 1, but a line, such that x is greater than -2. And you know what? I'm looking up here at this one, and this really should have been x is greater than or equal to -4 and less than or equal to 6. Do you see how I missed that? So let's make sure that we get that right. So let's make that to have a greater than or equal to, greater than, less than or equal to, all right? And then back to this one. So, but in this situation, x is greater than -2, but it's not equal to -2, because when x is -2, y is 0, which is not greater than 0, right? But x is also less than or equal to 6. Close curly braces. All right? So that's set notation. Now, on what intervals is x increasing? On what intervals is f of x increasing? On what intervals is f of x increasing? Well, from here to here is the function, and the entire time f of x is increasing, isn't it? So it's really the domain of the function. Okay, on what intervals is f of x increasing? F of x is increasing the entire time. So in set builder notation, let me try a different color, or in interval notation, it would be our domain written like this, from -4 to 6. And we would write it the same way that we did the domain up here. Curly braces. X is an element of the real numbers such that x is greater than or equal to -4 and less than or equal to 6. Okay? On what intervals is f of x decreasing? On what intervals is f of x decreasing? Is it ever decreasing? Never. It's never decreasing. So that's undefined or none. Okay? It's never decreasing. For what values, if any, is f of x greater than 3? When is f of x greater than 3? So let's see if we can find that first. Let's find f of x when f of x is equal to 3. Let's find when f of x is equal to 3. So we already actually found it. Do you remember? It was right here. Here's f of x is 3. Okay, that's when f of x is 3. So the question is, when is it greater than 3? Well, it's greater than 3 from there up, right? So if we were going to write this in set builder notation, actually let's do interval first. If we're going to do it in interval notation, we would say that x is 0, because that's what x is when f of x is 3. X is 0. That's where it starts, except notice that I didn't put a bracket. I put a curved brace because it doesn't include 3. F of x has to be greater than 3, so anything bigger when x is bigger than 0, right there, right there, right there, all those little spots along the line, but not on 0 when x is 0. All right, so f of x is greater than 3 when it's bigger than 0, so we put the 0 isn't included all the way until 6. And 6 is included, okay? Now let's write that in interval notation. X is an element of the real numbers, okay, such that X is greater than 0, okay? It's greater than 0, but not equal to 0. And X is less than or equal to 6. Closed curly braces. All right? So we've just described this graph, and we've described these intervals using set builder notation and interval notation. Okay? Let's do one more. Now it says, consider the linear graph f of t and the nonlinear graph g of t to answer questions 9 through 14. Okay, so we've got two different graphs of functions. Here's f of t, it's this linear one that starts here and ends here. And then we have this, it's actually a quadratic function, but this parabola, this kind of U-shaped function that starts up here and moves down and then back up, okay? And it's going to ask us some questions related to the two, all right? But before we do that, let's see if we can figure out a few things. Like, can you tell me what the domain of f of t is? What is the domain of f of t? What's the domain? Let's do that in orange. Let's first do it in interval notation, shall we? So the domain of f of t is going to be including -4, because we started here, and we went to 4, and it includes both of them, right? Okay, so we did f of t in interval notation. Let's do g of t. Let's do g of t in set builder notation, shall we? So we'll do that one in a different color. Let's do it in set builder notation. So we're going to say all t, okay, because t is our dependent variable. This is t right here, okay, and we're measuring the t's. So t is, let's see, element of, looks like because it's connected, it's all real numbers, such that, and let's see, t is going to be, it's basically going from here to here, right? Our x's or our t's are going from here to here, okay? And then, of course, they travel up and down the this y-axis or what this g of t axis. But we'll go ahead and just talk about t being greater than -4 and less than, greater than or equal to -4, less than or equal to 4. All right? So we've identified the domain. Okay? Now, let's see what it's asking us. It says, where is f of t equal to g of t? That means, where do they share the same points? Where do they share the same points? There's two places. Can you find them? Why don't you circle them on the graph? Circle them where they share points. It's where they intersect, isn't it? So here and here. That's where, when I put t in to f of t, I get the same answer as I put t in for g of t. So this point right here is -2, -1. So we're going to say f of t equals g of t at -2, -1. And they're also equal at this point. And what's that point? That point is 3, 4. Okay? Now, where is f of t greater than g of t? Where is f of t greater than g of t? That means what value of t, when I put in t, will the value be larger than the other? So that means when let's just try this point right here. If I put in the value of -4 for t, when I put in the value of -4 for t, I get on f of t, I get -3, because this point is -4, -3. But when I put in -4 into g of t, I get this point up here. So this is -4, 11. So in this situation, g of t, the value of g of t is greater than f of t, because when I put in the same value, when I put in the same t, I get a much larger number, right? But my question is, or this question is asking us, when is f of t greater than g of t? Well, we know that they're equal here, okay? And if I picked this one right here, again, this value for -3 is much less than this value up here for -3, right? See that? But what happens when I go over here, say, to this value? What if I say when t is -1? When t is -1, f of t is 0, right? And when t is -1 here, g of t is -4. Well, now f of t is greater than g of t. F of t is greater than g of t. So we know that right here, f of t is greater. I think if I go here, it's going to be the same thing. If I pick this point, 1, 2, and where's g of t? G of t is way down here, which looks like it's when t is 1, g of t is -4. So f of t is greater there. F of t is greater here. What about on this point right here? Suddenly it switches, doesn't it? Right here, f of t is 3. When t is 3, f of t is 5, but g of t is 11. So it's this section right in here. It's between this point and this point, right? Because what did we say this point was? We said this was 3, 4. And we said this point here where they were equal was -2, -1. So between -2 and 3, between -2 and 3 on the x-axis, or on the t-axis, when t is -2 to 3, then f of t is going to be larger than g of t, which ends up down here. So where is f of t greater than g of t? Well, we'll write it in interval notation. We'll say, let's see, we said -2 to 3. and it's not going to include them because when at -2, they're both equal. So remember, this is a point. This is not a point. This is interval notation. And let's write it again in set builder notation so that we remember. So we're going to say all t, okay, all t is an element of the real numbers such that, okay, t is greater than -2 and less than 3. All right? Now, the next question is, what is f of 0 plus g of 0? What is f of 0 plus g of 0? Well, we've got to first find f of 0 and g of 0. So f of 0, that means when x is 0, f of 0 is equal to 1. So f of 0 equals 1. And g of 0, when x is 0, g of 0 is right here, and that is -5. So what's 1 plus -5? -4. Okay? That was pretty easy, yeah? See if you can figure out what f of -1 plus g of -1 is equal to. What's f of -1 plus g of -1? Well, f of -1 is 0, right? Because here's when t is -1, f of -1, it's 0. And g of -1 is -4. So that's equal to -4. Interesting. Which is greater, f of 0 or g of -3? Which is greater, f of 0 or g of -3? Well, we know that f of 0 is 1, and g of -3, so let's see, 1, 2, 3, 1, 2, 3, looks like it's right about, let's see if I can get there, there. So g of -3 is 4. Which is greater? Well, 4 is greater, right? So g of -3 is greater than f of 0. And then graph f of t plus g of t from -1 to 3. And we're not going to do this one because you're going to learn about this at on our next video. But we've just done some descriptions of the graphs. We've done some interpreting of the graphs. We are getting very good at functions, and you've now learned a new way to describe intervals, not only using interval notation, but also now using set builder notation. And that's all we have for today. I'll see you in class.